everybody, and welcome to another wonderful episode of the Learn It, Turn It, Burn It, Torque and Drag miniseries. We are up to episode number 5 today. Thank you guys all so much for joining us. Brought to you today by Cougar Drilling Solutions. If you haven't already, go and check them out. So appreciative of them being a sponsor today. And yes, we will. Where did I put it? It's hard to miss. Oh, it's directly behind my monitor. That's why we will be giving away a drill bit today. But first, let me know where you guys are watching from. Love to be able to give give some people a shout out here on the show. Looks like everything is working over on LinkedIn. That is wonderful. Love to be able to double check everything. Let me know if you guys can hear me. It's always good to be able to know that the audio is working as well. So, wow, that came in kind of hot. So maybe I'll turn my mic down just a little bit. Mic is in the correct position. Okay. Yeah. So guys, if you want to be able to continue getting notified when we go live for this, when I put other stuff on LinkedIn and or for the Vidor Locksmith show, click follow or click the notification icon over on my profile page. Pretty simple stuff to be able to do, but it will let you know when we go live, because we've had a handful of people reach out and say, hey, when are you actually going live? When does it showing up? Where is it showing up at? If you want, you can just get a notification and LinkedIn will say, David's doing the thing. And there you go. You can jump on in. All right. Hold on just a second. We're getting some text messages here from crucial people who are probably going to be telling me can't have chat on YouTube. Okay. So something's happening on YouTube. Let's see. Tracy, would you check out what's on YouTube to see if we can... Oh. Okay. I can't see, but it looks like everything's working there just fine. Let me go over to the comment section, make sure everything's going there. Oh, yeah, we're getting stuff on YouTube. Okay, just making sure everything's good. All right, everything's good. Once again, Learn It, Turn It, Burn It, Torque and Drag mini-series, episode number 5. We've got the guys from Merlin here today to be able to talk to us. Brought to you by Cougar Drilling Solutions, right? Yeah, so let's say hi to a couple of people. Or I should say, let's say this. Where is my... I'm not organized this morning. I'm sorry, guys. I know I've got that sheet. Here it is. Okay. This week, Neil Armstrong with applications and Alistair Blair, who's also joining him. And then next week, Mitch with K&M Technologies, casing flotation, torque and reduction tools, casing liner, and kind of, yeah, that's next week. So don't forget. And then also this week on the Vidor Locksmith, Kenny Baker and Mike Holcomb from Cactus Drilling and Patterson Drilling, respectively, or Patterson Energy. New generation of floor hands. We'll be streaming live from the Patterson office with those guys. All right, let's say hi to some people. John DeWart tuning in this morning. Thank you for being here as always, sir. Tim's tuning in from Aberdeen. George, who won the drill bit last week. That one actually belongs to George when you get it sent off to him. Thank you for being here. Peter from Germany, thanks for being here. Robert Carrington, San Antonio. Brad Watson becoming the new #1 fan of the show, tuning in from Houston. Thank you for being here, sir. Mark Anderson, LinkedIn user from Iraq. The LinkedIn user, that person time travels faster than anybody. He said, Randy, this is like his 3rd week in a row. France. Florian says, hi. I want to know who here has not missed a live episode yet, or how many of the episodes have you seen thus far? Have you watched all 4? Or are you waiting to binge a whole bunch of the previous ones? All right, tuning in from Dubai. Thanks for being here. Mohammed from Egypt. Luis, watching his boss or colleagues. I don't know. Luis is here. Great guy. Zaid tuning in from Algeria, who got essentially his PhD thesis from watching the series here. So much respect to him. If you guys have not already, reach out and connect with this young gentleman who's doing, his PhD on, things that we find interesting. Great person to be able to connect with. Zad, good morning from Calgary. Mohammed says we're live in career. Thanks so much. Ian Birch tuning in from Woodlands, Texas. Thank you, sir. Louis Estrada from Germany. James from Harker Heights. Thanks, sir. Zad from Algeria. We're watching from Abu Dhabi. Debbie tuning in from Houston, Texas. And 2 weeks from today, she will be presenting an absolutely amazing resource to our energy. Biname from Canada, thank you for being here. Vipul from Kuwait. Mustafa from Ottawa. Let me see. Oh my gosh, there's like a gazillion of these. Okay, I'm gonna have to go through real quick. Durin, Randy, Debbie, Abbas, Randy again, Mauricio, Brandon Foster. Says greeting from let's get our Scotland on. Okay, Adrian, Osvaldo, Debbie again, Ian, Matt Williams. 4 of 5 for me. All right, that's what I'm talking about. Jeff Chestnut, and then Christian from Qatar. All right, guys, it is that time of the show. If you would like to win yourself a giant drill bit, right? Vidor Locksmith, we give away the little ones. For this series, we give away the big ones, right? If you want to win one of these, you need to be able to put in hashtag Cougar onto the screen right now. Need you to do that. Put in hashtag Cougar, as well as if you are typing on your computer screen right now, tag a friend in the comment section and let them know about this, right? Let them know about the show. Let them know that, we are covering some amazing stuff here in our industry with amazing educational pieces. So hashtag Cougar. While that's going on, we have a little clip from our sponsors. Check this out.
In any formation or section of a well, inconsistent drilling parameters and excessive shock and vibration may cause damages to the bit and BHA, creating the need for multiple trips and increasing drilling cost. Cougar Drilling Solutions developed a mechanical thruster to solve these problems. By using a lone stroke assembly to balance downhole mechanics and hydraulic forces, the mechanical thruster provides a smooth energy transfer to the bit, even in erratic situations. This reduces drilling dysfunctions and increases efficiency. Regardless of your application, we partnered with you to analyze the BHA, well profile, and drilling performance requirements. This ensures you get optimal performance from the mechanical thruster, so you can meet your drilling objectives the first time, every time.
There we go. Put in the hashtag Cougar right now and be able to get yourself a chance at winning this bit. Let me go ahead and get this part off of the screen. Oops, wrong one. That one back on the screen. There we go. Guys, D-Tech are going to be happy about that one. All right. So special thanks to our sponsors, Cougar. Right. Those are the guys that are helping pony up for this one. Let's see if we've got any more coming in. There we go. I didn't see anybody tag any of their friends in the comment section. That's a little disappointing. That's right. Let's see. Make sure. Yeah, no. Everybody's just going to keep this all to themselves. They're not going to tell anybody else about it. That's okay. Like, share, subscribe. Do all the social media stuff. Y'all seen Mr. Beast and all those enough. Y'all can help out. All right. Where is it at? Oh, I didn't even put it up there yet. Present. Share screen. Chrome tab. Giveaway tool. There we go. I'm just going to keep glitching until I hit the button. All right. Get this up onto the screen. There we go. All right. We'll give it another 10-second countdown. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And we'll draw. All right. 60 people entered in for today's drawing. See who wins the giant drill bit. And our lucky winner of the day, Mark Anderson. Thank you, Mr. Anderson, for tuning in. Shoot me a message over on LinkedIn to myself and or to Miss Tracy, and we will get you lined up with the drill bit. All right. Close that one out. And now we will bring on the man of the hour, Mr. Neil Armstrong. Thank you for being here, sir.
Thank you very much for inviting us, David.
Well,
where's Ali?
Sorry. Oh, there we go. All right. Let me. Do you want me to go ahead and bring on Alistair now, or is this?
Yes, please.
All right. There we go.
All right. Morning, guys.
Morning, Alistair. How are you, sir?
Not bad at all. Not bad. Afternoon here, actually.
That's true. That is true. All right. Well, then I will go ahead and turn it over to you guys. Y'all tell me what y'all need, and then I will let you guys run with it.
Excellent, great. Thanks very much. Thanks again for inviting us on, and thanks to Cougar for sponsoring the session. So my name is Neil Armstrong. I'm the engineering director with Merlin, and I've got with me today Ali Blair. Ali's our engineering manager for Eastern Hemisphere. So I've invited Ali along as well because Ali's been working with Torque and Drag for 20 plus years. In fact, we worked together offshore 20 years ago, where we were using Torque and Drag for surveillance. He's also been involved in developing our software and QA/QC's Torque and Drag on a daily basis. So he knows it intimately. I don't claim to know it all, but what I don't know, Ali knows. So together we know everything. It's not really true, but we know. He's here to laugh at my jokes as well. Good stuff. So what we're planning on covering today is application. So we are definitely not here today to baffle you with science. The objective here is to demystify Torque and Drag models for the user and to explain recommended practices related to modeling. So getting your inputs correct, making sure your assumptions are valid so you can get good usable outputs, and then displaying those outputs. So recommendations for reporting. So one of our objectives here is to encourage engineers to run models at the early stage of planning and not be intimidated by firing up the Torque and Drag software, and also to run it during the operations phase, which is often neglected. So running it for surveillance to give you, an idea of hull conditions as you're drilling. So I've intentionally used the term recommended practices rather than best practices. There's always an opportunity to improve, and we don't necessarily have a monopoly on best practices. It's our recommendations. We've been doing this a while, and we do it. Torque and Drag is still kind of our primary tool, day in, day out. So we've learned quite a lot about using it over the years. And we're here to try and share some of that knowledge and hopefully help you improve where you're using it. We'll also cover a bit on interpretation as well, so how we not only present the data, but how we interpret it and then draw conclusions from it and use it. And then I'll summarize at the end with sort of our top 13 key points. And then we'll have questions and answers. So first off, all models are wrong, but they are useful if the user can check they're valid, if our input assumptions are justifiable, and also if we understand the limitations of the model. And the objective really at the planning stage is to determine what modeled loads are. So we've got a different objective at the operation stage. That's our objective there is determining what our actual friction factors are. So the planning stage, we've got our planned well information. We're then making assumptions about our friction factors, which is based on offset wells. And then we're using that to determine modeled loads. Whereas at the operation stage, we're using the actual well information and the actual loads that we're recording to determine our actual friction factors. So we then feed that back to the planning stage in order to improve our database of offset friction factors to help us then more accurately predict loads. Because ultimately, we've really got two aims when we're using and applying Torque and Drag. It's to determine the margin between loads and limits as accurately as possible, so at the planning stage, but also at the operation stage where we're projecting forward. We're trying to see, as we're drilling, are we going to be within our operating limits when we're deeper in the well or when we're at TD? So as accurately as possible, we're trying to determine that margin between loads and limits. But we're also at the operations stage using friction factor trend modeling to provide us with an indicator of hole condition. So it's another useful bit of information to help us piece together the puzzle to determine what's going on downhole. So that's really essentially it from applying torque and drag. The operations guys are often a little bit cynical about torque and drag monitoring. Is considered to be a bit of an engineer's hobby, and but when we've got a model that works, when we've got actual data like this that plots on a profile. This is a hook load profile, a drag profile, and it's matching nicely. We've got a trend line there in blue, the actual data, and it's matching the model data nicely. And often when we can show that to the operations team, to the driller, to drilling supervisors, they'll look at this and think, actually, yeah, it does work. You guys can predict what's going on. And once we've got them on board, then we've cracked it. They then get on board with collecting good, consistent, usable data, and using it themselves to identify adverse trends. So we'll start off by looking at the inputs and some recommended practices related to the inputs. So the inputs are relatively simple. In fact, all models are pretty simple. Yes, the stiff string model is more complicated, but from a user's perspective, it's still pretty simple. There's a limited amount of inputs. So don't be intimidated by it. Get it fired up, get stuck in, run it at an early stage in planning. We can use some crude inputs and then refine them later. But basically, all we're looking at is a trajectory, including some assumed tortuosity, wellbore definition, which is essentially just the ID of the wellbore. And then we're looking at the string definition, which is the OD and the average weight, or the pounds per foot, as I've got on there, bullet point number 3. And then we specify what friction factors to display, which will be based on our offset wells, as I mentioned earlier, and then the mud weight, and possibly the traveling assembly weight, unless we're producing a tensile plot, in which case, rather than a hook load plot. And then there may be some friction adjusted intervals, which I'll talk about in a few slides. So essentially, there's only sort of 5 mandatory inputs. So it's a pretty straightforward process. So for friction factor selection, this is often one of the main assumptions. We always want to be displaying at least 3. We want to be displaying our low side, our most likely, and our high side. So if we've got some deviation, it gives us an idea of how significant that deviation is at the operation stage, and it also gives us an idea of sensitivity at the planning stage. How close are we to our high side and low side. And this is based on offsets. So the most appropriate offsets you've got, and we need to make sure that the assumptions are valid. So is it appropriate to use floated casing friction factors that you've gathered on offsets, or is it for a conventional casing string, so a casing string that you're running full, and then we have to account for outliers. So in this table here, we've got down the bottom of the slide, we've got some data that's been captured from offset wells while running a 905/8 casing string. We've got a maximum value there of 0.8. So one well on the slack off, it was running in the average value was 0.8. And then we've got but the average value of all the wells was 0.39. So we need to explain why that outlier is an outlier and it's not valid for our well if we're not going to use it. We can't just disregard it because the well design doesn't work if we use that, because the 9 5/8 won't go to bottom. So we need to know why it's an outlier in order to disregard it. And then for drilling, we'll use cased hole friction factor equal to open hole friction factor. If you've got high angle casing, the friction factor will not remain consistent within your casing because it will load up with cuttings. So you'll have essentially varying friction factor inside casing. And we also have to remember that the friction factors aren't necessarily the same for all operations. So just because we've got a 0.3 friction factor for pickup, with our 12 1/4 inch drilling assembly, that does not necessarily mean we're going to see a 0.3 for slack off. Now, if there's a huge variation between the two, then there's probably something wrong with the model, and we need to look and see if it's calibrated properly. But there's no reason it wouldn't be unusual to see a 0.1 difference between the two. And also, friction factors are not necessarily the same for all operations. So, of course, it was pretty obvious, but your friction factors are not going to be the same for slacking off to bottom with your 12 1/4 inch drilling assembly with 5 1/2 inch drill pipe in a high angle well versus running your 9 5/8 casing in the same. Because if you're using a soft string model, you're going to be the friction factors accounting for stiffness.
And Neil, we've got a couple of questions already. I could jump in and answer if you want. Yep. Okay,
yeah, that would be great. Yeah, it's difficult to stay up with the comments when
okay, no worries. So,
if you could do that.
Yeah, Peter Jorn Palton. So he's saying for offset data friction factors, you use only wells drilled with similar mud system and similar formations in case available. So yes, correct. When you're looking for offset friction factors with which to do your planning, really you just have to take what you can get. You want to use your closest offsets possible, both formation-wise and mud system-wise, as you say. But, you take the closest you can get. So, maybe you've only got maybe a nearby field with some different formations and a different mud system. So you've got to make the best of what you've got, but you have to make inferences. You say, okay, well, this is with water-based, for example. I'm going to be using oil-based, so you might want to, reduce your assumed friction factors based on that. But yeah, you go for the closest match situation you can. And then your follow-up question you've got there, you're asking about the influence of local dogleg severities from a whipstock, for example, 15 degrees per 30 meters. So are these implemented into the survey report? Okay, so yes, it's an interesting question, regarding the influence of tortuosity on the torque and drag model. If you have, something that can accurately reflect your whipstock exit, for example, if you want to put that in that extra survey point that reflects that 13-degree dogleg, then yeah, put it in. Will that give you a definite difference on your torque and drag result? Maybe, maybe not. That depends on a few things. It depends on, Neil's already mentioned the soft string and the stiff string model. You may see it more on the stiff string model. You may not really see it at all on a soft string model. But in general terms, I would say, a single dogleg like that would tend not to have too much of an influence, depending on the size of it. So if you've got lots of tortuosity, however, repeating, then yeah, you will tend to see quite a difference. So the question becomes how much tortuosity can you build into your surveys. So, but that's something you can play around with either actual surveys at low spacing, or you can do tortuosity overlays in your modeling and see what difference you get. At the end of the day, you're trying to replicate the real situation that you're seeing as closely as possible, validate that in the real world, and then you can feed that back into your future planning. So I'll try and be more concise in that in my next.
No, good. Thanks, Ali. As I see my staff has asked a question about cased hole equals open hole. Isn't the open hole friction factor higher since it's more of a rough surface? Well, yes, normally. I think really probably I need to explain that. What I mean by that is variable friction factors in cased hole and variable friction factors in open hole for drilling, rather than using a fixed friction factor for cased hole. So yeah, not saying they're going to be the same in casing as they are in open hole. I'm saying that you use variable friction factors, and that'll become apparent when we start looking at some of the charts.
Yeah, just quickly on that, we say that case for drilling, we tend to use average from top to bottom for drilling for a couple of key reasons. One of them being we're basically saying that the low side of the hole, the contact points are generally going to be seeing cuttings beds. So you've got your same interface, whether it's open hole or cased hole. That's one reason. You're also not really in a position to have nailed down the clean cased hole friction factor at that stage, and you're not really going to be seeing it so much anyway. So it's just a convention we use for the drilling. We'll just make it average from top to bottom. When it comes to tripping or running casing or liner, then yeah, we can split out. We normally do split out cased hole and open hole.
Yeah, and that's not really unique to us, though, is it? I mean, that's a fairly standard method. Okay, and then the last point on that slide is beware of reducing average friction factors. So I've been involved. So when we're talking about, we pick one friction factor for a whole section, that we've recorded in these tables. It is possible that, so that's an average friction factor for the entire interval that you have string across. I've been involved in wells where we've had a very long high angle 9 5/8 interval, and then a very short 8.5 inch drop into the reservoir. And at the start of that whole section, the friction factor was higher. So the torque while drilling out the shoe was higher than when we were deeper in the 8.5 inch hole section, because the casing polished up, the friction factor reduced as we were drilling ahead. So there, just be aware that the friction factor could be higher, shallower in the well than at TD. So the next slide, I'm talking about tortuosity. So there are different methods for accounting for tortuosity, but essentially, we're accounting for all unplanned dogleg. If we had the ability to drill the directional profile as planned perfectly, then we would have no tortuosity in the well. We would just have dogleg that would be planned. So essentially, tortuosity is any unplanned dogleg. So a simple approach that you might take at early stage planning is to have a standard input in your software model that you use for when drilling with a motor versus drilling with a rotary steerable tool. So clearly you'll be adding a little bit more tortuosity if drilling with a motor. And then a more advanced approach would be to match the tortuosity with offset wells. So you're essentially calibrating your well against offsets. So using the same tools in a similar interval, what tortuosity was observed on those wells, and then you calibrate your tortuosity or artificial dogleg that you're going to add to the model accordingly. And then yeah, string definition. So Ali, do you want to talk us through this one?
Yep, apologies, just finding my unmute button. Okay, so this is just to demonstrate how we typically will model the BHA when we're entering the drill string into our torque and drag model. The most important thing to state that the most important element of that drill string to get right and accurate is your drill pipe, okay? Because that is by far the longest part of your drill string. When it comes to the BHA, we typically condense that down to one line as an approximation. So as you can see here, from the model on the left with the parameters box, and on the right, you've got a BHA listing that was used in this case. And that, highly detailed, 13 component BHA, lower BHA, I've called it, has been condensed down into one line called the lower BHA. Now, is that valid? Yes, absolutely. This is a soft string model. The only thing really that matters in generating that hook load plot that you see there is the weight per foot. So we need to put in the adjusted weight per foot of all the components. So back to the yellow box there, the lower BHA. So what we've done, we've got on the right-hand side of the BHA listing, we've got cumulative weight of the BHA and cumulative length. Just divide one by the other and you'll get your weight per foot for that whole section of lower BHA. And that absolutely accurately models that part of the string. Done similar for what we'll call the upper BHA, which is basically a combination of the heavyweights and jars and a few other subs, highlighted in green there. And then at the bottom of the BHA listing and at the top of the parameters box here in red, that, as I said, is the most critical part of the drill string. That's your drill pipe. It's a single line. If you get the adjusted weight of that you've input wrong by, say, even 0.2 pounds per foot, that can make a huge difference to the accuracy of your model. Again, because it's such a huge part of your drill string. So if you make a slight error in the weight of your BHA, which is only 150 feet, then not so much. So it's just an illustration why it is normal and perfectly valid to condense the BHA part of your drill string, as long as you get the weights as accurate as you can. So, and the next slide. So one area where you can see implications of approximating, let's say, BHAs with something else, you could see a difference in your buckling resistance, your buckling limits when you run a buckling chart. Okay, so in this example here, what we've done, this is a rig that basically for their push pipe and running a liner, they're using what they call hybrid stands of drill collar and heavyweight. I think it's 2 joints of heavyweight with a joint of drill collar in the middle. Okay, now given that you've got about 500 feet of that, if you were to model that section of pipe component by component, it can be quite laborious. It's pretty detailed, and then when it reports it, it's going to be a huge, big, long list of components. When you do so, on the right-hand side, you'll see the effect on the buckling limits. It's got spiking in and out. On the left-hand side, what we've done is we've just approximated it. You've done an average weight for that stand, given the blend of the heavyweight and the drill collar, and just put that in as one line for the whole section that it covers. Now, you could say that the latter case is a gross, careless approximation, but the point I'm trying to make here is that actually the upshot is the same. Well, you've got maybe slightly different distances to buckling in each of these sections, just above 1,000 feet. The upshot's the same. What's critical in this case is where does the section of drill pipe end and begin? Or where does the section of stiffer push pipe cover? Because, so the detail of the buckling limits in that zone isn't so critical. It's where it starts and ends. So again, it's entirely valid to approximate these different elements of pipe.
Great, thanks, Ali. Yeah, and then just quick one on traveling assembly weight. Often at the planning stage, you might not know what rig is going to be used. You might not know the traveling assembly weight. So at the planning stage, input can just be 0 for your block weight or traveling assembly weight. In which case, you've essentially produced for a drag plot, you've essentially produced a tension plot rather than a hook load plot. And it actually also makes it easier to see when you're approaching block weight or negative weight, because that's at 0 tension when you've got 0 tension at surface, rather than it having the block weight shown. So that's a perfectly valid approach. And then other assumptions that we may need to make are related to friction reducing tools. So they could be swivel tools, which is shown the first picture on that slide, this one here. So that's that tool was used to produce the plot over on the right, or was used in the operation that produced the plot over on the right. You can see all the blue dots are filtered surface hook load data. So you can see when we're in slips, making up a new joint of pipe, we're close to the block weight, and then when we're running in, so these markers that are shown are actual slack off weights. The red ones are actual slack off weights, and the blue ones are slack off weights with rotation. So rotating above the swivel tool. So you can see that with this this operation, the liner was able to run in without the benefit of rotating above the swivel. But you can see occasionally rotation was done just to check to see and validate the model for future operations and for longer wells, and to see what benefit you'd get from the tool. And you can see you get quite a significant increase, almost 100K at TD of additional hook load when running that liner in hole. So that would then, capturing this data then allows you to more accurately predict your load for the future operation, longer well. And then we've got non-rotating protector clamped onto the drill pipe, shown here, actually a Western Well Tool super slider. And then at the bottom we've got a Weatherford low torque and drag casing centralizer. So it provides axial drag reduction in cased hole with these rollers that are in contact with the casing, and then these rollers here are in contact with the casing that's inside the centralizer. So that produces a torque reduction. So main point here is we want to be conservative with the benefit that we're going to get from these tools at the planning stage. So not overestimating the benefit. And we need to remember that it's local. So it's we'll only get benefit over the interval. And also when it comes to sort of the NRPs or these roller centralizers, you're not going to get much benefit in open hole, and also some of them some NRPs you're not going to want to run in open hole anyway. So basically, you've got to be just aware of where you're going to get benefit from them and be conservative with your assumptions. But still useful tools. So on the reporting side, we can spend a lot of time making sure our inputs are appropriate, they're accurate, they're justifiable, and then we can waste a lot of that time and effort by producing poorly presented charts. And this is an example of a poorly presented chart. We've got here, we've got torque and drag on the same plot. We've got a poorly calibrated plot because our actual off-bottom weights are not on the model. So we've only got one friction factor plotted for both torque, one for pickup and one for slack off. So there's multiple things wrong with this, and we'll go through some recommended practices for reporting data. Another point worth making is if you're an engineer and you're producing these models, you know it intimately, and it's easy to assume somebody will look at the chart and they'll see, or they'll draw the same conclusion that you will. But that's not often the case. You have to draw people's attention to the key points on the plot and make sure everything's displayed with an appropriate description. So, and that kind of relates to the operation as well. So this chart here, the header on it is surface torque plot. But what does that really mean? You have to look into the parameters box here to see that it's actually drilling torque. So it's on bottom torque, and there's an assumption being made for bit torque. So it's not off bottom torque. So we have to make sure we properly define what operation we're showing. Now, we may even have a hook load plot that's slack off. It looks like it's straight slack off and pickup weights, when in fact it could be slack off with rotation and pick up with rotation weights. So we just need to make sure that we know that we clearly define what the operation is. And the operation does make a difference on the loads. If we look at this example here, this was the Friday Haggler last week. We've got on the left a 2D well plan. So it's basically just a long lateral, an 8.5 inch hole. Actually, it's not. It's in 7 7/8 inch hole, down to 22,000 feet. And you've got 9 5/8 casing set at about 10,500 feet. And if we assume a 0.2 friction factor, you can see on this torque profile, and this is off bottom torque. You can see we've got about 16k at surface. So how much torque are we going to see when we're at TD if we throw in a 180-degree turn? So let's say we've got a lease line constraint, and halfway down that lateral, we put in a 180-degree turn, and we drill back towards the rig, and we still TD at 22,000 feet. So our off-bottom torque is going to be pretty much the same. It's about, with a 0.2 friction factor, it's about 18k. And you can see that turn is around this point in the well. It provides virtually no additional drag or additional torque. So whereas if we were looking at the back reaming torque at TD when the string's in tension in the straight, then it's a completely different story. So with a low friction factor of 0.2, and we're talking about 20k, whereas with the U-shaped lateral, it's about 25k. And then the more friction we've got in the well, so the higher the friction factor, the more difference we're going to get. So in the 0.4, it would be, that's approaching 50k, whereas we're up about 60k. Oh, no, we're not. We're up about 70k. So you can see now the influence that turn's having. So point is, the operation is important. It is going to make a difference to your loads. So what another situation where that could be relevant is if you're looking to see what your maximum torque is, say TD in your 12.25 inch hole section. If you were just to look at your drilling torque, then you'd be underestimating your maximum anticipated load because your highest load would be when you're back reaming and the string's in tension. So in order to understand why that makes a difference, then Ali will give you a quick explanation as to how these side forces are generated.
Okay, so just a little bit of a recap how where side forces come from. What I'm going to do actually is I'm going to temporarily take off my virtual background so I can do a little demo. But if you see, look at this side force plot that we've got here. You see we've got marked on there where the side forces have been modeled by the torque and drag software. You see in red color, you've got high side forces, and in the blue, you've got the low side forces. So you can see there's a very high amplitude, high side force zone around that first build up. Okay, so you may be well aware as to the reason for that, but that's basically, no, what way round are we here? That's basically due to the tension round a curve. Okay, so if you look at this little tube here as being like a build-up BHA, imagine obviously you've got your drill string has got tension. It's going to have tension all the way up the string. So what happens when I apply tension to this curve? It pulls it into the high side. Okay, so particularly, well, in all models, but in a soft string model, your side forces come purely from the weight on the low side plus tension or compression round a curve. Okay, so if it's tension round a curve, you're going to see this. I'll find my camera. If it's compression round a curve, you're going to push it into the low side of a build. Or if it's a drop off, the tension is going to pull it into the low side, compression is going to push it into the high side. Okay, so that's where side forces come from. And you can see in that plot that your predominant side forces here are coming from that initial build section because it's high up in the well, and that's where your highest tension is. So that's going to be your predominant. And that relates back to the example Neil was showing you there, as to why you're going to see a different situation in that U-shaped lateral when you start pulling out, because you've got all those high side forces around not only, well, the build section, but also your turn in your lateral.
Yeah, excellent. Thanks, Ali. Great. Yeah, and I mentioned earlier about how important it is that the model's valid and that the user can check the model's valid. So the key things are to display the inputs that have been used. And one of the most important parts of that is the actual adjusted weight used for the string. Sometimes what you'll see on plots in the parameters box, it'll be just, it'll state the string description, the drill string description with the nominal weight that goes with it. It doesn't necessarily mean that's being used as the input for the adjusted weight of the string in the model. But if it's not shown what's being used, how do you know the model is valid or not? The operation as well specified on the chart. As I mentioned earlier, whether it's on bottom torque, off bottom torque, or whether it's straight pickup slack off, or it's pickup slack off with rotation, and the model type, whether it's a soft string or a stiff string model, and the calibration. So, somebody's going to immediately look at the plot and check to see, are my rotating weights, my rotating off bottom weights on a hook load plot, are they aligning with my rotating off-bottom model curve? And if not, then the model is not calibrated properly, and therefore it can't really be used to determine valid friction factors. And then another really important thing on the plot is specifying the operating limits clearly. As I said at the beginning, one of the primary aims of applying torque and drag modeling is to determine your margin between your operating loads and your operating limits, which means we need to properly display our operating limits. And it's good exercise anyway. It's good practice to clearly state these so everybody understands what they are and what the basis of them is. It's not unusual to be involved in an operation whereby the rig team's using a different limit for, say, drill pipe tensile limit than the office team's using. So if we state what it is on the plot, then that's more likely to come out. No, that's not what we're using. Or you'll sometimes see, we're assuming that the operating limit for an operation is maybe the drill string, or even for tensile, and then we'll find out that the rig's derated and it's actually the rig. So the more clearly we can state it, the better. And this is showing a torque profile plot for a tapered string where we've got a lower limit down hole than at surface, in which case this is absolutely critical that we're showing the limits on this plot, because the whole purpose of it is to determine whether we've got an acceptable margin between our loads down hole and our operating limit down hole. And then other good practice is when you're doing comparisons, is to clearly show them on the same plot, so we can see the benefit. So this is showing a string, 7-inch liner actually, a floated option, so fully floated liner, not the running string, and then a floated liner with an inner string to give you the ability to circulate, and then a conventional where it's full, and then this allows you to see clearly the benefit of one versus the other. And now, displaying actual data on charts at the operation stage. So important things here are clearly labeling the data. So we know what it is, so we can differentiate slack off weights and pickup weights from reaming weights. One thing that is guaranteed to irritate me is on a tripping plot, displaying pickup weights and then using the same marker for them when you start rotating at a hole and reaming at a hole. Because it's a different operation, you should be using a different marker to display that data. It can be misleading. If somebody were to come, whenever you're producing these plots, it's always worth keeping in mind, what is somebody going to need to know if they come back and look in the archives, if they're planning a similar well and they're using this well as an offset well, what do they need to know? And they're going to need to know whether you were actually reaming out of hole or whether you were pulling the string on elevators in order to determine whether that friction factor is valid or not. Because essentially, this model here is showing straight pickup in red and straight slack off in blue. So they're not valid if you're rotating the string and picking up or rotating the string and slacking off. So reaming. And then also clearly differentiating between breakover weights and your dynamic is valid on this model. And then annotations. So the annotations are just basically adding the story to the chart. And we need to be putting annotations on charts that relate to all factors that influence friction factors and the actual data. So, what key things are going to influence our friction factors? Well, additional tortuosity, any formation changes, bed height change, instability, a fluid lubricity change, or some sort of operation change, connection practice change. So that's more like the connection practices. It's more like related to the bed height as well. It's whether you're spending more time reaming on connections or doing some additional circulation. So that's going to affect the bed height or the solids in the well. When we talk about bed height, the assumption is it's cuttings. It could well be cavings as well, or even some other solids. It could be, if you've got barite sag in the well, it could be high gravity solids that are influencing it. But most of the time we're talking about cuttings. So all of those things that listed there are going to have an effect on your friction factors. So if there's any change that you're aware of that relates to any of those, then it's useful to put some sort of annotation. Like here we've got on the plot, connection time increase. It would be more useful to know, well, what actually happened there? My assumption is that they spent more time circulating on connections, and then the friction factor dropped off, both for pickup and slack off. So it's just really painting the picture. So when it comes to interpreting these plots, we can't really do that effectively unless we understand what affects the friction factors. Because essentially all we're doing is we're looking at the plot, we're seeing our actual data's deviating from a previous trend line, consistent trend line, and then we're looking at it, doing a bit of an investigation to determine why is that occurring. In order to do that, we need to know what things are going to be affecting, what affects my friction factor. In which case, we need to have a pretty solid understanding of what friction factors are and what they are not, which is where Ali is going to help.
Okay, so yeah, just taking a little bit of a step back, first of all, looking at the fundamentals of the torque and drag model. As Neil says, let's understand where these friction factors are coming from, how it all works, and that should massively help in your interpretation of the model, of your monitoring, because you know what the limitations are. Okay, so first of all, it's all based on the fundamentals of dynamic friction. So as you see in the picture here, I don't know if anyone was involved in an experiment at school where you can demonstrate the principle of sliding friction by pulling a weight along a bench with like a spring balance as shown in the picture here, some kind of force gauge. And you can quickly demonstrate that the frictional force required to keep the object moving along the bench is directly proportional to the weight of that object. Okay, or put more generally, the frictional force is directly proportional to the normal force. So that's the force perpendicular to the contacting surfaces. Okay, and in the chart at the bottom here, it demonstrates that relationship, the direct proportionality between the frictional force and the normal force. And the ratio between the two, or you could say the gradient of the line, is the coefficient of friction, sometimes known as mu, as shown here. And you can also represent that relationship in this little triangle down here. So if you want to work out mu, the coefficient of friction, which is in the bottom right of the triangle, you would divide the frictional force by the normal force. If you wanted to work out the frictional force, you would multiply the bottom right left by the bottom right, or vice versa. So you'd multiply the normal force by the coefficient of friction, mu. Okay, so it's a simple proportional relationship, and it perfectly describes basic sliding friction. The important point to note that this coefficient of friction that's derived from this, that you can demonstrate in a lab, or not even as clean conditions as that, coefficient of friction depends purely on the two surfaces in contact with each other. Okay, so if it's wood on rubber, that's a certain coefficient of friction. Change either one of these two materials, you'll get a different coefficient of friction. So that's basically it for basic sliding friction and coefficient of friction. If we go to the next slide now, we now look at what we're doing with our downhole torque and drag model. So what it does, whatever the torque and drag model is, you get some fairly basic ones. You know, the soft string model is fairly universal, has been about since the early 80s pretty much. You get some stiff string models these days that are quite a bit more sophisticated and complex. Regardless, all models use this basic assumption that your torque and drag, your drag force is following exactly the same relationship as shown in the sliding friction slide before. Okay, so we're basically saying that your drag is directly proportional to your side force. Okay, you can show it in exactly the same relationship here. Okay, in this case, the constant of proportionality, instead of calling it the coefficient of friction, we call it the friction factor. Now, why? Is that semantics? Is there a difference? Well, yes, there's a difference here, and it's reflecting the imperfection of the model, if you like, the assumptions that we've made. Because in this case, our friction factor, instead of being this lab measured frictional force over your lab measured side force, it is your implied drag. So what is your drag? It's basically your hook load when you're picking up minus your neutral string weight. So that extra weight that you're experiencing when you're picking up the string, you're assuming that's your drag. Okay, and the same when you're running in, your hook load will be less by a certain amount, which you're assuming is your down drag. Okay, so basically you're putting that at the top of your triangle. So the reason they're not the same is the apparent drag that you've derived, it's mostly due to sliding friction, but not necessarily all due to sliding friction. You can have other things that will contribute to that, such as ledges. Significantly, cuttings loading will give you a higher drag, but that's not to do with sliding friction, and therefore not directly proportional to side forces. So, and the other thing that's not as controlled as you might like it is the assumption of the side force. So the side force obviously is worked out by the computer at lots of incremental bits down the string, but it's worked out by a model, whether that be the soft string model, the stiff string model. They both do it in slightly different ways. And as Neil's slide at the very start said, neither of them are absolutely perfect. All models are wrong, as he said. Okay, but the ones that we use are pretty useful. Okay, so the upshot of that is it's just to have the understanding that no, friction factor is your apparent drag divided by your side force, cumulative side force calculated by your model. That's what it is. And that's not the same as coefficient of friction, which purely depends on the two materials in contact with each other. Okay, so as we said at the bottom here, you know, whether you're doing this with the soft string or stiff string model, it's actually it's remarkably close to reality. And the one thing when you will see it deviate, and usually the biggest thing that makes it deviate is the cuttings load. We can actually use that to our advantage. And we do use it to our advantage. That's the means by which we can monitor downhole condition using friction factor. Now, we need to be aware that it's not just the cuttings that can make the friction factor drift. There are lots of other things, but we use, in conjunction with everything else we're observing, we can make pretty strong inferences as to what's going on downhole. So,
Great.
Hope that's clear enough.
Very good, Ali. Thanks. So another point on interpretation is, we can't just use this friction factor or torque and drag interpretation in isolation. We need to look at additional non-torque and drag related data. So, for example, we see a torque increase. First thing we're going to look at is, has the RPM or the weight on bit changed? So basically, the drilling parameters are critical. We can't draw any conclusion with just what we see on the drag plot or a torque plot without checking the drilling parameters. If we see a drag divergence, has the driller changed? Is the AD now on, or is the tool pusher now on the brake? Is he doing something different with the way that the data is being collected on connections? Has the flare rate changed? Are we not accounting for hydraulic uplift in the model? Or is there a hook load calibration change? And again, if we've got a drilling torque change, has the formation changed? So it's just understanding all these additional parameters and factors that are affecting what we're measuring here, torque and drag, and also understanding the limitations of what the model does not do. And it's always worth reminding people that the model does not predict static drag. No, there's no model that's going to predict static drag for you, or what your breakover is going to be. It's always, we're plotting, what we're showing here is dynamic drag. Showing on the same charts your breakover is very useful in order for identifying when the hole is getting sticky and your risk of differential sticking is elevating. It's picking up the warning signs for that are critical, but the model is not going to predict what it is, what it's going to be. The only way you're going to get an idea is just, again, looking at offsets. What type of deviation am I getting, or what's my breakover like on previous wells with similar fluid in the same formations with a similar string. They're not going to give you any indication of instability or hole enlargement. And they're not going to tell you what your cuttings bed height is. They'll give you an indication. Often an increase in friction factors is related to an increase in bed height, but it's not going to give you any indication of how high that bed is. So they have their limitations. It's fairly crude, but it's very useful because of its simplicity. And then sort of interpretation here, we've got an example of a plot. So I'm looking at that plot. I've got my my parameters box is populated, showing all the data. It's valid. I've got a nice calibration all the way down to TD. But at some point, my slack off weights stop. I've got intermittent slack off weights. So what's happening there? So really, if we look at the plot, and we can see, if I were on a higher friction factor up here on slack off weights, then it shoots off to the left, which is an indicator that we have buckling in the string at some point. This plot is not going to tell you where the buckling is occurring in the string. It's just showing that on that higher friction factor, buckling will start. Now we go from friction factor to friction factor where I'm starting. And you can see your hook load picks up, the pickup weights increase, and then at that point we no longer have the ability to slack off. So it does appear to cross a number of friction factor lines to get to that point. But yeah, we know there's some additional drag in the hull. Exactly what's causing that drag, we don't know. And maybe look at some of the annotations, and that might help me determine that. And then we see here from the hook, the pickup weights, they drop off a bit, friction factor reduces, and then we also start getting the ability to slack off on connections again. And then this is an example of a floated casing string, where we've got, initially here we're putting in air-filled pipe, and then we have some slightly heavier, so 53.5 pound per foot air-filled pipe, and then we start filling above the selected flotation collar. So then we've got mud-filled pipe. So this is showing the running sequence, not the order in which the string's configured when we're at TD. It shows the sequence, i.e. what you're running in hull first. Anyway, point on this one is, what happens here? We go from having a hook load of about 160k to suddenly 260k. We get an extra 200. We get an extra 100k hook load. So when we look at the data labels, yes, this is sort of filtered hook load data, but it's pretty. Without any additional information, it's difficult to determine what actually happens here. So what really happens here is we start rotating. So they start rotating the string in the hull, and which transfers some of that axial drag to rotational drag or torque, which is the way I prefer to think about it, rather than saying you've broken friction, because you don't just eliminate all friction by doing that. You're effectively transferring it to rotational drag or torque. So it would have been so much easier to interpret this if the data had been labeled correctly. So this is slack off hook load, and then this is rotating hook load, and then it would be very simple to determine. And then these brown dots are showing your minimum hook load, which is basically your breakover. So that's what was required to get the pipe moving when coming out of slips. So yeah, my recommendation is to produce these plots for somebody in future to look at, and to be able to figure out what was going on when they're planning their wells and using your well as an offset. And then finally, some key takeaways, key points. Yeah, don't be intimidated about firing up the models at the early stage. Don't keep putting it off because you think it's going to turn into a massive job. Get it fired up, use basic inputs, and then refine them later when you do your detailed planning. Use a basic survey plan, basic tortuosity, and then see what it looks like at the early stage, and then refine it. And then ensure assumptions are valid, and initially conservative for friction factor reduction. Tools, especially complete the feedback loop. So with consistent data collection, get the operations team on board. Yeah, these things do work. It is worth putting the effort into consistently collecting good data, so we can then feed that back and use and with improved planning with better offset well data. Showing the results and explaining what it's all about to the operations team is the way to go to get them on board. And then properly annotating the charts to highlight the key points, just filling in the gaps, giving that story, like the plot that I showed before. What one comment on here, or correctly, using different data markers for that data, it would have made it pretty obvious what was happening. Show the inputs clearly and properly, i.e. properly describe what adjusted weight you've used for the model, so somebody can do a validity check easily. Know your limits. So yeah, make sure, remember one of the key points is we're trying to identify that margin between operating loads and operating limits. So we need to clearly define what our operating limits are, and be rigorous about using different markers for different operations. Clearly showing what our breakover torque is, what our drilling torque is, and what our off-bottom torque is. And the operation is important. So if you want to know what your maximum torque is going to be in the whole section, then you don't run an off-bottom torque model at TD. Run your back reaming from TD, or rotating with the string in tension. Even if you're not planning on back reaming the whole section, you still will need to be rotating with the string in tension at some point, inevitably. And then understanding the friction factors is absolutely fundamental to being able to do valid interpretation of these charts. And interpretation of the charts is only really possible if you're using other non-torque and drag related data. So the drilling parameters, has the flow rate changed, has the ROP changed, has the weight on bit changed, because all of those things are just going to have a huge effect on these loads that we're observing and plotting. And then understand the limitations of the models. They all have limitations, but if we understand them, then they're usable, and it'll ensure we don't draw incorrect conclusions from the data. So, have I missed anything, Ali?
No, I think that, well, obviously, yeah, you've missed lots of things, Neil. I mean, it's a huge topic, and we can't possibly hope to cover it all, do it full justice, but we like to think we've given you a reasonable outline of the practical usage of torque and drive modeling, why we need it. It's not just we still get the impression sometimes some rig crews still think it's just a fanciful engineer's toy and nothing to do with them. I sometimes get told that frequently, but so the point of this is hopefully we're all on the same page here. That's it can be an ultra critical tool. Are we going to be able to rotate at TD? Even when we thought we could at the planning stage, now we're actually in the well drilling. We're seeing what our actual friction factors seem to be. So is it still going to work? Sometimes, no, we're not actually. We're going to run out of torque. So we've got a couple of days to try and do something about that. So that's one of the key points of it. And then, of course, there's a downhole monitoring using the friction factors, the imperfection of the model that we pointed out to our benefit, and see what the hole condition is like. See, is it loading with cuttings, etc. Can we improve in the hole cleaning? So really powerful tool if you understand what's going on and you use it properly. So I think we've got quite a bunch of good questions I've seen here. I've collected some of them.
Should we start with the most recent one there at the bottom? We've got we've got a few minutes to go through some questions.
So
what
Eric
was
says,
what? Yeah.
Go ahead.
Sorry, David.
What is the best
so
first indicator of differential sticking? Change in pick up hook load.
Yeah, I'd probably say changing torque, but it depends what you're doing first to get the string moving after it's been stationary. But with hook load, then you've also got to account for stretch. You've got to account for potentially cuttings avalanching at some point in the well. All high angle wells have got a low angle part and a transition zone through the avalanche. So you could have cuttings that are influencing that hook load as well. Whereas they're going to have less of an influence on torque. So probably the cleanest and neatest way to see it after a period of stationary pipe would be with breakover torque.
Yeah, we just emphasize that. Remember, differential sticking is a static condition. So what you're looking for, it's not your average pickup or your average off-bottom torque. What you're looking for is the initial, when you've been static and you start rotating or picking up. So what we always advise is a good practice when you're taking weights before connections, your weights and your torques before connection, particularly when you're in a differential sticking. Risk zone is always monitor the breakover. Plot your breakover weights and torques along with your averages that you're recording. And you can often see if these two start to diverge more, then that's a clear sign of potential onset of differential sticking. The differential sticking tendency is increasing.
Oh, here, let me put that presentation back up there.
Yeah, and then we've got LinkedIn user monitoring 4 different rigs in 17.5-inch hole section. My pickup weight is less than my slack off weight, up to 2,000 meters. Inclinations less than 20 degrees. This one has sheave friction flashing all over it. All the key indicators there. You know, you're shallow because you're drilling 17.5-inch hole section. And well, you've told me down to 2,000 meters, low inclination, and the classic sign is your pickup weights sometimes overlap with your slack off weights, or exceed your slack off weights. So yeah, that's definitely shift friction there.
Yeah, so I see one of the other in the comments, one of the other users, my Sam, has come up with the same answer himself. So he's obviously familiar with that. And yeah, that's very much what it looks like.
And so some models will correct for that as well, won't they?
Well, yeah, just a quick note on that sheave friction. So what's it coming from? It's basically if you are taking your hook load measurement from the deadline, then your measurement is susceptible to the friction around all the sheaves. Okay. You probably won't notice anything when you've got, good inclination in the well, because your well drag is much more than your sheave friction effect. But strictly speaking, if you're aware of it and if you've noticed it at the vertical part, then you should correct for it. There are spreadsheets you can correct for it. We've got it built into our software as well. You can make a correction, and strictly speaking, you should apply that correction throughout because it's still present throughout. Just because you can't see it anymore because your well friction is taken over, that discrepancy is still there. So strictly speaking, you should keep it going. Do people always? No, only when it's visible.
So is that a constant value throughout, or does that value?
Yeah. Okay. It's going to be constant because it's a function of where you're measuring. It's a function of the derrick and your sheave line setup. It's one of these ones that can be hard to get your head around. What's actually happening. The way you're measuring at the deadline is actually going to be lower when you're picking up than it is when you're slacking off, when you're lowering the blocks. Because
the only way to completely eliminate it, the only way to completely eliminate it as a problem is to use a torque and tension sub instead of deadline tensiometer. So you're essentially measuring, rather than block weight and hook load, you're measuring tension at the top of the string, or torque
stuff like that.
Yeah.
So here's a follow-up question from Simon. Is it better to correct the hook load sheave friction or apply the deadline correction to the measured values?
I'm assuming that you're asking, is it better to correct your measured values or is it better to correct the model? My answer to that would be, I don't think it really matters. As long as you're aware of what you're doing, the correction that you're applying, it should be the same thing. When we looked at incorporating the correction into our software about a year ago, for example, we ended up figuring out that it was easier to correct the values as they come in. So we can apply the correction to the measured values. We could equally have applied the correction to the model. So we just found it easier the first way. So either way, I would say, if you've got a different opinion on that, I'm happy to discuss.
Yeah. And actually, there was a question that's kind of related to that from Ari Wahayudi. Calibration weight, is that for adjusting the rotating weight to match the actual? Yeah, so on this slide, in the parameters box, there's a calibration weight here. So basically, if you do make any changes to calibrate the model, we really need to state what they are, in order to be able to reproduce the model later, if you're using it as a planning basis for an offset. So yes, essentially the simple answer is yes. It's shifting all of, not just the rotating of bottom weight. You'd have to shift all of the model data. So there's really just two fundamental ways of calibrating the model. One is modifying the adjusted weight of the pipe. That's in the hole, or making a straight shift of all of the data to align everything. And if the adjusted weight of your pipe is incorrect, then you'll see gradually, as more and more pipes in the hole, you'll see you're deviating from the model more and more, in which case a fixed calibration shift across won't rectify that. You need to change the adjusted weight of the pipe.
But yeah, it's a good question. So as Neil said at the beginning, one of the most important things with a hook load plot is make sure your rotating weight is calibrated. So your actual rotating weights are lined up with the green neutral line in the middle of the model. You could say that this calibration shift is a little bit of a cheat, but how we get away with that cheat is that, we're okay with that as long as it's automatically reported in these parameters. That, yeah, this has been shifted by however much. And then we would also say that, you should have a reasonable, valid reason for that. You should understand, okay, I tried to adjust the weight to get a good calibration, but still, think this is the best it can get. We're still applying a calibration. One reason could be hydraulic effect. So some torque and drag models account for hydraulic effects, hydraulic uplift. Others don't. So you will see a shift through hydraulic effects, depending on, of course, your annulus size, your AVs, etc.
Excellent. Any question that you guys saw that you want to go to next, or just start at the top?
I suppose Florian's asking, do you agree with the operator on specific well-defined parameters, procedures to gain reliable measurements, or do you take it the way they do? I think the question's related to how we're taking the pickup and slack off and rotating off bottom weights and off bottom torques for the models while we're drilling. We often have to give a little bit of guidance, but the most of the time it's just making sure it's consistent and that there is a procedure. There's often some discussion about whether you do it with pumps on or pumps off. If the model accounts for hydraulic uplift, then as long as you're accounting for it in the model, or if the flow is low enough that it really is having negligible effect, then it doesn't really matter. Now, one benefit of doing it with a small amount of flow is then you have no you can counteract any negative effects of swab when you're taking your pickup weights. But you have to do it with the same for pickup, slack off, and rotating. Are there any others you fancy answering there, Ali?
I was just having a look at, there was a couple of latest ones come in. Some interesting ones potentially. Maybe I should better go ones I definitely understand before I try and interpret some of the new ones. Right, so going up to the top. So soft string or stiff string, Merlin's recommendation, one of the early questions. Okay, so my take on this is going to be for most what I would call normal drilling situations, let's say normal. Now that's normal is very different for different people in different parts of the world, so it's a dangerous word to use. But still, like for most situations, the soft string model is sufficient. What I would say, if you're going to, if you want to look at some results from a stiff string model, look at the soft string as well at the same time, and trying to understand the differences, see what's actually happening. But in most situations, you're going to get pretty close results with both. It's interesting when you compare the two. It's not necessarily what you might expect. If you say with the stiff string model, you're getting, you might assume that you're going to get more side force because you're taking into account the stiffness of your string to give you additional side force. But often you might find that actually your implied drag is less with a stiff string model. And the reason for that would be that it's actually not following every little curvature of the drill string. You've got discrete contact points. So it can actually make your implied drag go the other way. But in most cases, the differences can be small.
Yeah, and we often end up using a soft string model, and a lot of operators do, because their historical friction factors, their friction factor database is built up of soft string friction factors, and they don't want to go back and re-hindcast with the stiff string model, so it tends to be easier. My final point on this one is I would recommend watching Stefan Manan's presentation from last week, so H&P drill scan on stiff string versus soft string, and then you'll get a pretty good understanding of the differences between the two.
There you go. All right, I'm gonna just start firing through these pretty quick. Can you predict increased friction factor based on inclination due to cuttings?
Well, yeah, I mean, I suppose if you've got, as soon as you start getting inclined hole above the avalanche zones, and where you start getting cuttings building up in stationary beds, then you could probably safely predict at that point you're going to start getting an increase in friction factor. Yes.
So just to refine that slightly, sorry, what we tend to do when we're drilling a high angle hole is we start to, when we're using friction factor data to monitor the whole condition, the whole loading, we'll usually, we'll let the data points settle down, if you like. You're into the avalanche zone, you've drilled, a few 100 feet or more, and you start to see where your pickup weights or your slack off weights are sitting in terms of a friction factor line. Okay, let's say it's 0.2. They're all sitting on the 0.2 line. So that is your base case drilling equilibrium bed height, if you like. Okay, so that's it really. Yes, you're not going to see as much potentially when you're low angle, maybe 20 degrees, but you're using it practically, and you see, right, okay, now I'm in an inclined hole. That's my kind of clean hole friction factor. That's what you're practically using it for. And then when you start seeing trends trending up above that, you're saying, right, okay, it looks like the hole is starting to load a little bit. Maybe we should do something about that. So that's the extent to which you can use it, rather than predicting what friction factor you're going to get due to cuttings at a certain inclination, or even what's my bed height. Who cares, quite frankly? What you need to monitor is it increasing above equilibrium.
All right, so we've got 10 more. We're gonna have to rapid fire some of these so we can get Neil out of here in time. So Rod asks, slide 6, you mentioned a varied friction factor in cased hole due to cuttings accumulation. Is this not also valid for open hole and any software that runs variable friction factor while drilling section? And I'll pull the slides back up because I think you're there.
Yeah, so I think all we mean by saying, use cased hole friction factor equals open hole friction factor is essentially using, really what we mean is use a variable friction factor for cased hole and a variable friction factor for open hole. So the alternative is assuming a fixed friction factor for cased hole, and that might be valid if you're running a casing string or a liner, because you've got the same material, it's metal all the way down to your shoe. And if you've cleaned it up properly, then and you don't have much influence of solids in there, then you should have the same friction factor all the way down. So in that case, it might be valid to do that, but you need some idea of what it is. But while you're drilling, the cuttings don't care whether they're in, or they don't know whether they're in open hole or cased hole. So if you've got high angle casing, they will settle there and they will influence that friction factor, which is why you need to have variable friction factors. So that's all. It probably a better way to term it is use variable friction factors while drilling for cased hole and variable in open hole.
Yeah, and I think the last part of that question says any software that runs variable friction factor while drilling a section. Well, I'm not sure what you mean by run variable friction factor, but what we're doing here is we're displaying the range of friction factors. In this case, from 0.5 slack off up to 0.5 pickup at 0.1 increments. You can do whatever variations you want, but that's a typical setup we would use. And from that, when you plot your actuals on there, you can then read off what the friction factor is. So what we don't do, and what nobody should really do, is try and predetermine the friction factor when you go drilling. Don't drill with a fixed cased hole friction factor because you don't know that it is that. So just go with variable and then you'll see what the friction factor is. Yes, at the design stage, you have to assume a friction factor in order to predict your loads to check that you're going to be okay. But drilling, it's display the variable. And I think most softwares do that, are able to display a range of friction factors like that. That's what you need to be using when you're using it while drilling. Hope that answers your question.
Little follow up here. Why cased hole friction factor equals open hole friction factor for drilling? I understand that an engineer can work with that, but why is cased hole friction factor not equal to open hole friction factor wrong or problematic?
Okay, I think
I know we've been covering a lot of this, but I wanted to be able to get at least acknowledge that we did get the question. So
yeah. So I think that's basically. So I think he's asking, why is it wrong to say the cased hole friction factor is not equal to open hole friction factor? Okay, so basically what we're saying here is when we're drilling, we're just going to assume that you've got a full range that is going to be the same in both. One of the reasons is you've got cuttings beds all the way up the hole, in open hole and in cased hole. So let's assume that interface between the pipe and the hole is pretty much the same all the way up. Yes, there'll be little differences. There'll be parts where you're actually contacting the high side, etc. But it's a fair assumption. Let's just keep it simple and not separate out the cased hole friction factor. Once we've cleaned the hole and we're running something else in, like casing, for example, if we've got a pretty good handle on what the cased hole friction factor is, then we can zero that in for the next operation, and then that allows us to be a bit more accurate with subsequent operations. Hope that works.
All right, next one from Alistair Pundler. So from your experience, not including stabilizers and large OD tools in the BHA is all good, but only for soft string models.
Yes.
Okay. So I'd say yes for soft string models. That is correct. Even for stiff string models, how much of a difference is like individual stabilizers in the BHA going to make?
And watching Stefan's.
Uh-oh. Is Neil
Jumped
cutting
out of
out?
sync there.
We'll recycle pumps and let him come back to life.
I think. Am I back?
Yeah. You're back now. Go ahead.
Good. Okay, yes.
And
A simple
we
answer
like
is
you.
yes. And watching Stefan's presentation, am I still loud and clear?
Yeah.
Yeah,
There's
going.
just a little bit of delay.
Don't lose your momentum.
Yeah, it keeps buffering. So yes, watch Stefan's presentation from last week, because he makes it clear that once you start using a stiff string model, then obviously tubular stiffness is accounted for, which is going to make a big difference if you're putting in whether it's a stabilizer or if you're just approximating it as a collar. And it takes into account radial clearance as well. So yeah, it's going to have much more, defining the BHA will have much more of an influence on a stiff string model and negligible influence on a soft string model.
All right, next one. Peter, using a packed BHA with full gauge stabilizers will create the same results as a BHA entered without stabilizers for soft string. For stiff string, a minor difference will be calculated for torque results with the different contact points for short length of BHA compared with long heavyweight drill pipe and drill pipe section. Question mark.
Yeah, I think.
Yes.
I think he was really answering the question from before rather than posing a question.
Okay. Fair enough.
But yeah, he's right.
Okay. Randy, on to the next one, slide 8, discussing adjusting weights. Have you ever seen an error when using the spec sheet adjusted weight and actual average adjust weight in the field?
Slide. Yes.
Yep.
Yeah. And actually the obvious thing that we immediately think about is just drill pipe, but you see this probably more with casing than you do with drill pipe, and it can become quite problematic if you're floating casing, where you've got very low adjusted Boyd weights. So it could mean a difference. So it's a slight variation in your assumed adjusted weight versus the actual adjusted weight can make the difference between it being neutrally buoyant and positively buoyant. So it's trying to pop up out the hole. And there's a good SPE paper by, well, it was Statoil at the time, now Equinor, where they ran a 10 3/4 inch string and couldn't get it in the hole because it was like trying to push a beach ball underwater. It kept popping up, and they ended up having to suspend the well and rig up snubbing slips and clamp the thing in the snubbing slips and push it in the hole. So yeah.
But yeah, further to that, the first thing as well to check is, have you got the correct spec sheet? And I saw a comment or a question from somebody else. I can't find it now, but I think it was very similar. It was asking, but what about when your tool joint length is different, in the field is different from that shown on your spec sheet? Well, in that case, you need to enter the tool joint length as it actually is. If your spec sheet is telling you lies, you need to try and find out reality as close as possible and enter that in your model. Get the right spec sheet. That's a good start.
All right. Hold on just a sec. Let's get this next one here. Slide 8. How do you model any torque and drag reduction tools in the BHA in this way of modeling? What about stabilizer gauge? Can it be modeled in this way?
Okay. So what we do, certainly in our torque and drag software, and I think in most, what you tend to do is you define a portion of the drill string which has some kind of friction factor modifier. So you can say, okay, for this section of the string, let's say where you've placed drill string protectors, torque reducers. You can say for this section of the string, my torque is going to be half what it is elsewhere. So that's how you do, torque modifiers. Your question about can you do that for stabilizer gauge? No, not really, unless you're saying that these stabilizers are actually going to increase my torque friction factor. Now, I wouldn't want to run any stabilizers that are going to do that. Or let's say they've got Teflon blades and you're going to claim that they're actually going to reduce your torque friction factor. Again, I wouldn't really believe that. But yeah, in that case, yeah, you can.
That's what the spec sheet says.
You can create that friction modification if you believe it.
All right, we'll jump on to the next one here because we've got a handful more to go and we want to get Neil out of here. Slide 9, having heavyweight drill pipe between drill colors can compress the heavyweight drill pipe and possibly buckle it. How was the field result for this hybrid stance?
Okay, so that's an interesting one. Neil, if you do you want to go to the slide that was shown? I think it was the one after this, where that example was shown with the hybrid stands. So actually, what you've got to kind of learn to do, and learn to, when you run the model, understand what it's saying and trust the model. So what this model is actually saying is the heavyweight itself is not going to be crushed by the collars either side. What that's implying is that they're going to be buckled. What we've actually got here is the compression in the string is shown by these blue lines, these light blue lines on the right-hand side. And what we're interested in is how close they are to the buckling limit lines. In this case, the blue line is your sinusoidal buckling limit, and the maroon is helical. So that's telling you the story. Whether you think hybrid stands are going to crush themselves or not, this is telling you what's actually going to be happening. So yeah, in this case, it's your drill pipe that's going to buckle first.
All right. Right on to the next one. Zaid, our PhD student. Can the torque change in surface be an indication for a kick?
Yeah, I can't see that. I'm not sure what influence an influx would have on the torque.
Well, except by changing the hydraulic situation down there, you're changing the weight of the string. So yes, changes in torque or drag could come with a kick. You'll probably see other things first, but yeah, you could see an apparent change in weight. Think about hydraulic uplift. It could well be the case. If you suddenly got a gas influx into the string, into the annulus, for example, you've got a different weight situation.
There'd probably be other indications that happened prior.
Yeah.
Or maybe not, before any gas is migrated, possibly if there's a significant amount down there, if it changes the weight significantly, you're going to see a difference in contact forces, difference in torque and drag potentially.
Very interesting. All right. We got 3 left here. Question for what? Would having an increasing friction factor while drilling to account for poor hole cleaning and cuttings accumulation yield a better and more accurate model?
Yeah, that so essentially you'd be changing your friction factors to account for drag increasing. I mean, that's not really what we're trying to do. I mean, that's not making the model more accurate. It's the fact that we do change from one friction factor to another that's allowing us to use the model. That's what makes it so useful. It's allowing us to see then that something has changed downhole, and providing we can eliminate some obvious things, then we can often draw the conclusion that it is cuttings building up.
Yeah. So our most accurate model is showing, let's say, a clean hole. It's showing what it's going to look like if it's only sliding friction. And then when cuttings loading is happening, you'll see the divergence from that model. So that's how it's useful, as Neil says.
One of the last two here, Adrian asks, what would be your approach for modeling the pull force needed to expand an expandable liner when the tension limit is from the drill pipe specs?
Okay. So I've not actually done this with an expandable liner where you need a certain pull force. We often encounter where you need a certain set down weight. So I'm assuming it's a similar situation. Some need pushed, some need pulled. Okay, fine. The way we model that is we basically model the string only down to the liner packer or whatever it is, and we will apply. You run a tension profile plot, an elemental plot with your buckling limits or your tensile limits on the other side, and you will shift it. So if you're applying a slack off, if let's say you need a 60K set down, you just shift it 60K to the left and see if you're starting to encroach in any of the buckling lines. Similarly, if it's tension you're applying, you shift it to the right and see how far you are from exceeding any of the tensile limits on the drill pipe. And it's typically going to be at surface where you're going to be encroaching on your tensile limits. Unless you've got a tapered string, you also need to be looking at your crossover, because that's another potential where you could be exceeding the tensile.
Yeah, very good. And I can take this last one.
All right, go for it, sir.
Yeah, so can you explain the visible effects on the friction factor curves by having downhole agitators on the drill string? And if somehow the software model can calculate the friction factor if the agitators are changed from on to off. So that's from Cadel Martinez Sanchez. Yes, you can model it. However, only NOV can model it. They've got a proprietary software package that models the effect of agitators on friction reduction, so on torque and drag reduction, with different placement positions of an agitator and a shock tool in the string. So yeah, NOV can do it. If you want to know more about it, talk to Danny Perez and Roman Shea at NOV, and they'll help you out. And a lot of the engineers have the software package that'll help you predict that. And I know that because we helped them develop it.
Well, there you go. All right. Well, thank you guys so much both for being on the show today and being able to bring our industry a little bit more education on torque and drag. So huge thanks to you guys there at Merlin, and also huge thanks to Cougar for sponsoring this episode. If you haven't already, go check out their website. Follow them there on LinkedIn. They're doing a lot of really cool stuff. I know that they're going to be doing some huge and amazing things for OTC. So be sure to stay tuned for that. Mr. Cadel Martinez says, thanks. A handful of other people had said, thanks for the answers. Ari said, thank you. All right. So everybody is very appreciative. All right, everybody, if you have any other questions, feel free to still put them there into the comments or send them out there. If you haven't already, follow Merlin, follow Cougar, follow Neil and Ali on their respective LinkedIn channels. If you want to, you can follow me. It doesn't bother me. Like, share, subscribe, all that other stuff. Remember, this Friday, we've got Kenny Baker and Mike Holcomb talking about the new generation of floor hands at interviews this week for the Vigor Locksmith Show. As well as next week, we got Mitch Abu Hussein with special operations sponsored by WWT, casing flotation, torque and drag reduction tools, casing liner and drill pipe swivels, and then casing and liner cementing loads. Mitch with K&M Technology. So another round of excellent presentations. This was episode number 5. We've got 3 more left to go. Like I said, Mitch, Debbie, and then once again with Brandon Foster. Getting even more people in here saying, Louis says, gracias, excelente. Mustafa says, excellent. Thank you, Neil. Thank you, Ali. Thank you, David. Brad Watson says, outstanding. Thanks. LinkedIn user says, thank you, Merlin. David. Bazad says, great presentation. Thank you, Neil, Alistair, David. And then Sam says, thank you as well. Thank you guys all so much for watching. We really, really do appreciate it. Tune into the Viewer Locksmith Show. Tune in next week. We'll have another episode coming up on this Torque and Drag mini-series. Anything else from Neil or Ali? Anything you guys would like to share with the audience?
Just thanks, David. And thanks, Tracy, for helping organize. And also thanks to Cougar for sponsoring.
And any other questions, guys? If anyone asked anything that we didn't answer, you can find us. Ask away, no problem.
Or tune into the Friday Haggler. There you go. Follow Neil on LinkedIn. He's always got something that he's posting on Fridays that I completely do not understand. And one of these days, I might actually know something or be able to contribute in some small way. That's it from here, guys. Thank you guys all so much. We really do appreciate it. And as I always say, know your industry.